The aim of this lab is tracking the motion of an oscillating string mass system, comparing the measured motion with a computational model, and plotting energy changes computed in the model. The principles and models involved in this lab are the Newton's laws of motion, including Newton's momentum principle and the position velocity update formulas, as well as the force of gravity near the surface of Earth, the spring force, the average speed for non-constant forces, the energy conservation principle, and the kinetic, spring potential, and gravitational potential energies. The computational model was found to predict the motion of the oscillating spring mass system with reasonable accuracy. The energy principle was demonstrated computationally. In equilibrium position, the spring force equals the gravity force. However, when not in equilibrium, the resultant force causes acceleration and tends to restore the system to its original state. According to the energy principle, considering that there is no work done on the system, the change of energy in the system is zero. Then the sum of all energy changes in the system should be equal to zero. For this experiment, we consider the system to be the mass, the spring, and the Earth, and there not to be anything in the surroundings. On tracker, the origin and reference system are set up when the system is in equilibrium. The distance from the fixed end of the spring to the center of mass of the object is measured. For the computational model, we first configure the initial conditions such as the mass of the object and its initial position, and we set up the constants for the acceleration of gravity near the surface of Earth, the spring constant calculated from the period of oscillation measured and tracked with the following formula, and the relaxed length of the spring. The stretch of the spring is found by subtracting the center of mass position from the relaxed length of the spring, and the energies from the elements in the system are calculated. Then the initial energies of the system are defined, and the net force is calculated. After that, the velocity and the position of the object are updated using the momentum principle. After that, the length of and stretch of the spring are updated, and the energy changes in the system are calculated for the time step. When running the code, the following plots are generated. The measured and predicted motions are very close. They follow the same pattern and both are harmonic oscillations. However, there are some differences in the amplitude of the model and the experiment, and also on the period of oscillations, which seems to decrease on the exposition for the experiment. Also, the changes in energy are plotted against time. Some sources of error are that the damping seen on X and Y position data are caused by external forces not accounted for in the model, mainly air resistance. Also, the damping of the spring oscillation along L hat also due to loss of energy in the form of heat because of material stress, among other interactions. And there are slight deviations in tracking due to the size of the mass. As there are no external agents, the work and the heat transfer should be equal to zero. Then the change in energy of the system should be equal to zero. The plot shows that the sum of all energy changes is always zero, so the energy principle is satisfied by the computer model. The period of each oscillation is estimated by measuring the change in time from contiguous graphs on each plot. Doing so, it is found that both periods are very close. However, the period of oscillation the motion of an oscillating spring mass system can be modeled with reasonable accuracy through the momentum and energy conservation principles. The system is found to behave in a non-idealistic manner, as the plot shown that the system is damped, therefore losing energy in the form of work due to external agents not accounted for. The energy principle has been demonstrated computationally by estimating the sum of the changes of energy.